in the last section of Module 5, we are going to take a look at graphs of rational functions. So first we're going to define what a rational function is. And a rational function is a function made up of rational expressions. So for example, you can have y equals 1 over x. That's the most basic rational function. We can also have it in the form f of x equals x plus 1 over x squared minus 1. That is also a rational function. It is made up of a rational expression. For a rational function, there are some very key important parts. The first one being a vertical asymptote. And I'm going to abbreviate those VA. So vertical asymptotes occur when the denominator equals 0. Just like when we were determining when our rational expression was undefined, or the values we couldn't plug in for the domain, that's exactly what a vertical asymptote is. It's the value or values that are excluded from the domain. So in a graph of a rational expression, when you're looking for where the vertical asymptote occurs, you're looking for where you had to pick up the graph. You're looking for that x value where it approaches that x value, but it never touches it and it never crosses it. So this line here is our vertical asymptote. And vertical asymptotes are always written in the form x equals, because they occur at x values, and then whatever that x value is. And from this graph, it's the value of x equals 3. So that tells me that my denominator of my function, I don't know what the numerator is, but I know the denominator has to contain x minus 3. In order for it to have a vertical asymptote at 3, the denominator has to be x minus 3. Based off this graph, I don't quite know what the numerator is. It could be 1. It could be pretty much anything at this point. Okay. So what we're going to do now is we're going to determine where rational functions have vertical asymptotes. And we're going to find our answer algebraically, and we can verify it graphically by using Desmos. But it's not necessary, but it is an option. So if we have y equals x minus 2 over x minus 4, just like when we were looking at section 1, I only care about the denominator. So I'm going to do x minus 4 equals 0, and I'm going to add 4, and there's a vertical asymptote at x equals 4. It is very important that you remember the x equals for a vertical asymptote because it is a vertical line. It is a line, it is an equation, it has to have the x equals. For our second equation, we have y equals 2x over x squared minus 25. So I care about when x squared minus 25 equals 0, which I'm going to factor as x minus 5, x plus 5. Each of those gets set equal to 0. And we end up with 2 vertical asymptotes. One at x equals 5 and one at x equals negative 5. So there can be multiple vertical asymptotes. There can also be none. You aren't required to have a vertical asymptote, but there can be 0, there can be 1, there can be 2, there could potentially be 3. We're not likely going to look at any examples where there are more than 2. The most common examples you'll see here are none, 1, or 2. All right, so the next thing we have to look at is something called a hole. And a hole occurs when a factor cancels in a rational function. So for example, if I have the function x plus 1 over x plus 1, x minus 1, I have the factor x plus 1 that cancels. So that value, I typically, if I were solving for where there's a vertical asymptote, I would say, oh, there's a vertical asymptote when the denominator equals 0. But if it's something that cancels, I can still technically plug in the value and get out a number, but I'm not supposed to. So x plus 1 equals 0, which means x equals negative 1 is a hole. Because if I plug negative 1 into my equation, I'm going to get negative 1 plus 1 over negative 1 plus 1 times negative 1 minus 1, and I'm going to get 0 over 0, which is 0. So I'm going to end up with a number, whereas if my numerator were just 1, I'd end up with 1 over 0, which isn't allowed. So a hole is a special case where it makes the denominator 0, but it also likely makes the numerator 0 as well. So it's not a vertical asymptote. All right, so what we're going to do is we are going to find where the graphs have a hole, if there is one, and any vertical asymptote. So what I need to do is I need to factor my function. So I'm going to have x minus 2 over x minus 2, x plus 2. Okay. And I'm going to have the x minus 2 cancel, so that tells me I have a hole where x minus 2 equals 0, which means I have a hole at x equals 2. It also tells me I have a vertical asymptote, specifically when x plus 2 equals 0, because that's the only thing left in my denominator, which is at x equals negative 2. So our second example, f of x equals 2x squared minus 50 over x plus 5. First thing I'm going to do is factor out my 2, and I get 2 times x squared minus 25 over x plus 5. Then my numerator is going to factor some more as x plus 5, x minus 5, all over x plus 5. So now the x plus 5 is going to cancel, so that tells me I'm going to have a hole when x plus 5 equals 0, which is at x equals negative 5. Now, since that was the only thing in my denominator, I don't have a vertical asymptote now. So my vertical asymptote is none. The last thing we're going to talk about are horizontal and slant asymptotes. So horizontal and slant asymptotes occur in one of two ways. So horizontal asymptote, so I'm going to start with horizontal, is a line of the form y equals b that the graph approaches but never touches or crosses. A slant asymptote is very, very similar, except it's a line of the form y equals mx plus b. So it's a linear equation, a linear line that the graph approaches but never touches or crosses. So unlike vertical asymptotes, in which a rational equation is not required to have a vertical asymptote, it will always have either a horizontal or a slant asymptote. Every rational function has one or the other. You can't have both. You can only ever have one. And I'm going to talk about how we find those. So there are three things we have to look at, and that tells us what type of asymptote we have. So the first one is when you have a rational function where your numerator and denominator are the same degree. So I'm going to abbreviate numerator and denominator. So numerator and denominator are same degree. And when that happens, you have a horizontal asymptote, which I'm going to abbreviate, where y equals the division of the leading coefficients. And I'm going to abbreviate leading coefficients as LC. So in an example, that would look like, so if I had y equals 2x squared plus 3x minus 7 over x squared minus 1. I just made that up. These are both have the same degree. These are both degree 2 because their highest exponent is an x squared. So they are the same degree. Their leading coefficients, so then that tells me my slant asymptote is y equals, the leading coefficient is the number in front of that biggest degree. So in the numerator it's 2, the denominator it's 1, so I get horizontal asymptote of y equals 2. The second type is when the degree of the denominator is greater than the numerator. And when that happens, you have a horizontal asymptote, specifically of the form y equals 0. So every time the degree of the denominator is greater than the numerator, then it's always y equals 0. So that example, I'm going to put y equals x minus 1 over x squared minus 1. So the degree of my denominator is a 2. The degree of my numerator, it's not written, but it is a 1. 2 is bigger than 1, so there's a horizontal asymptote of y equals 0. So we've talked about when they're the same, and we've talked about when the denominator is greater. So the third case is when the degree of the numerator is greater than the denominator. And this is the case where you have a slant asymptote and you have to perform long division. All right, and I'm not going to do an example of that here because it's not like a nice shortcut like it is with the first two examples we looked at. So we'll look at an example of this on the next page. So we're going to find the horizontal or slant asymptote. So our first one is y equals x over x squared plus 1. So I have to know the degrees of them so I can figure out if it's a horizontal asymptote or a slant. So if I'm looking, the degree of my denominator is 2. The degree of my numerator is 1. We just didn't write it. So that means the degree of the denominator is greater than the degree of the numerator. And when that happens, it's a horizontal asymptote at y equals 0. And I'm done. Okay, the second example, I have an x in the denominator and an x in the numerator. So in this case, the degrees are the same. So I'm going to divide my leading coefficient. So I'm going to have y equals 2 over 1. So this is also a horizontal asymptote at y equals 2. So those are the two easy ones. Let's take a look at a slant asymptote example. So in this example, the degree of my denominator is 1. The degree of my numerator is 2. So the degree of the numerator is greater than the degree of the denominator. So this is where I have a slant asymptote. So I have to do long division, and I really only have to do at most 2 steps. So when I set it up, x minus 4 is on the outside, x squared minus 3x plus 1 is on the inside. So I'm going to divide. X squared divided by x is x. Now I'm going to multiply. I get x squared minus 4x, which I'm going to subtract. The x squareds are going to cancel. Negative 3 minus negative 4x becomes addition, and I get x, and then I bring down the plus 1. My next step, I'm going to do x divided by x, which is 1, and this is where I'm actually going to stop. I don't need to do anything else because I don't care about the remainder when I'm doing a slant asymptote. All I care about is the x and the y-intercept. So my slant asymptote is at y equals x plus 1. I only care about the x term and then the constant that comes directly after that. I don't care about the remainder, which is all of the remaining part of this process. All right, so let's go ahead and put everything together and graph a rational expression. So we have y equals x minus 7 over x squared minus 1. So the first thing I'm going to do is factor it. So I get x minus 7 over x plus 1, x minus 1. So I'm going to go through all of my steps. So for whole, there isn't one. Okay? Nothing cancels from factor-wise from the numerator and denominator, which means I have 2 vertical asymptotes. I have one when x is 1, and I have one when x equals negative 1. Okay. Next, we're going to determine whether or not we have a horizontal asymptote or a slant. So the degree of my denominator is 2. The degree of my numerator is 1. So the denominator is greater. So I have a horizontal asymptote, specifically at y equals 0. The last 2 pieces of information that will be helpful in graphing this are the x and y-intercept. So when we're trying to solve for the x-intercepts happen when the numerator is equal to 0. So I'm going to take x minus 7, I'm going to set it equal to 0, and my x-intercept is at x equals 7. So that's the point 7, 0. The y-intercept is going to happen when I plug in 0 for x. So all I care about are the constants. So the constant in the numerator is negative 1. Constant in the denominator, negative 1, which is also going to give me 7. So I have a y-intercept at 0, 7. Okay. So when I'm finding the horizontal asymptote, the x-intercept, and the y-intercept, I want to look at the form before it was factored. When I'm looking for the whole, if there is one, or the vertical asymptotes, I need to factor my equation. So let's put it together and graph it. So first I'm going to draw my horizontal and vertical asymptotes. So y equals 0 is the x-axis. And then we have x equals 1. and x equals -1. All right, then we have our x-intercept at 7, 0, and our y-intercept at 0, 7. All right, and then if I want to figure out what it is doing, I need to also get a couple points. So I'm going to plug in a couple values for x to figure out, what it looks like in the negatives and like the rest of the positives. So let's suppose I plug in -5. So I'm going to go down here and plug in -5. So what happens when x equals -5? So I'm going to get y equals -5 minus 7 over -5 squared minus 1. That's going to be -12 over 25 minus 1, which is -12 over 24, which is -1/2. So that's roughly about here. Let's try negative. So that tells me what it looks like, because I can't cross the y equals 0. So that gives me an idea of the way this is going. It's going to go down like that. Okay. Then I have to figure out, all right, what's it doing between -1 and 1? And this one's a little bit harder to know because I have to plug in a fraction for x, because I can't actually plug in -1 or 1 because they don't work. So I need to plug in like 0.5 or -0.5 to figure out, is it going up or is it going down? So I'm just going to tell you what happens when I plug in -0.5. You get 10. So I know that it's going to be going up. So it's going to look like this on this side. Okay. And then lastly, I'm going to plug in a positive x value. And I'm going to plug in +5. So we're going to get 5 minus 7 all over 5 squared minus 1. And we're going to get -2 over 25 minus 1, which becomes -2 over 24, which is going to give us -1/12. So I don't need to know exactly where -1/12 is. All I need to know is that when it's a +5, it's negative. So that tells me it's going to come down and go up, kind of like that. Roughly. Okay. And you can verify it with Desmos. You can graph this in Desmos and you will see a graph that looks very, very similar to what we have on our paper. So let me know if you have any questions about graphing rational functions, whether it relates to wholes, vertical asymptotes, horizontal asymptotes, or finding x and y intercepts.